We're looking at grade 11 nomenclature now. So what's a little bit different from grade 10, coming out of the element or the intermediate grades, is in grade 10 you were taught you're looking for ionic compounds, you're looking for covalent compounds. We're breaking up the covalent compounds now into polar covalent and pure covalent. So there's kind of a subcategories, two subcategories within that. What you're looking for, first of all, in determining this, is if you have polyatomic ions in your compound. If there's any polyatomic ions, then it necessarily has to be an ionic compound. There's no ands, ifs, or buts about it. If you have a situation where all the atoms are the same, then the compound has to be pure covalent. If you have an electronegativity difference, which we talked about in the first unit, then you have a compound that could be polar, depending on where it lies in that spectrum. Could be ionic, depending on where it lies in the spectrum. Could be pure covalent. All right. So when you have two different atoms, you look at the electronegativities of those atoms, and you calculate the difference in those electronegativities. Depending on where they fall in this spectrum, dictates where they're going to be in terms of pure covalent, polar covalent, or ionic. If it's between 0 and 0.4, then you've got a situation where you've got a pure covalent compound. If it's a really, really, really small difference, then you may as well say it's pure covalent. If that electronegativity difference is between 0.4 and 1.7, lying on that scale, then you're going to find you have a polar covalent compound. So what happens there is the electrons are still shared between the atoms. However, they will spend more time around the one that's more electronegative. And as a result, then you have a difference or a distribution in charge. One end of the molecule becomes slightly negative and the other one slightly positive. And so as a result, then you get that polarity effect. If the electronegativity difference is greater than 1.7, then you have an ionic situation where the electrons essentially leave the one atom and join the neighboring. And as a result, then you get the formation of ions, and therefore it's an ionic compound. Then, of course, once you've decided what kind of a compound you've got to name it accordingly. Remember, covalent compounds use the appropriate prefixes, which indicate how many of each of the atom there are in the compound. If you have an ionic compound, you may need to use Roman numerals in order to indicate what the charge is on the cation. Multivalent cations in the transition metals and some of the lower section of the green box there, the P block, they will have the ability to form more than one possible cation, or more than one possible charge on the cation. And as a result, you need to indicate what that charge is. We use that Roman numerals to do that. You'll notice that some of the periodic table, especially in that old grade 9 and 10 one, that there are some elements that they derive their names from the old Latin names. You notice the symbols don't make a lot of sense. Symbols like K for potassium or Na for sodium. How does that work? And that's because they actually, those symbols are based on the old Latin names. And here are a list of the Latin names. And you will be required to know these, and especially the ones with the double stars here. Those particular elements are still used in some of the older texts, and you may encounter them in future years, so you may as well get to know what they are. The classical naming method works a little bit differently than our IUPAC method, which we use today, in that back in the day, really there were only a maximum of two charges known for most of these elements. And so as a result, there are only two forms that are accounted for in the naming method. So the higher oxidation number is given an ic suffix, and the lower oxidation number is given the us, OUS suffix. So here's how this works. For binary compounds, let's say we take lithium chloride, for example. The metal goes first. It's given the name straight off the periodic table, and then the non-metal comes afterwards and is changed. The ending is changed to an IDE. When we are writing formulas and naming ionic compounds, remember we need to consider the oxidation number, or the charge that the cation has and the charge that the anion has. And when we put them together, we have to put them together in such proportions so as the overall charge is zero. We call this the zero-sum rule. So for water, for example, here, we have hydrogen has a 1 plus charge. There's two of them there. And oxygen has a 2 minus charge. There's one of those there. And so the 2 plus minus 2 is equal to 0. In class, we go through a few. Sodium and chlorine, for example, becomes sodium chloride, NaCl. Calcium and sulfur becomes calcium sulfide, CaS. And oxygen and aluminum, aluminum oxide, Al2S, or O3, sorry, Al2O3. The classical system, though, uses an ic or an us, as I said earlier. So if I take iron and iodine as an example, iron can be either a 3 plus or a 2 plus. Iodine has a 1 minus charge. And so the iron 3 plus becomes, because it's the higher oxidation number, becomes ferric iodide, and the iron 2 plus becomes ferrous iodide. With the IUPAC system, we use Roman numerals instead, and the Roman numeral tells us what the charge is. So for the iron 3 plus, it becomes iron 3 iodide, and for the iron 2 plus, it becomes iron 2 iodide. What we have to make sure that we understand is this Roman numeral is not this subscript. That's really important. So Cu2O, the classical name for that would be, well, the charge on this copper is a copper 1, right? 1 plus. So it's copper 1 oxide, and so it's going to be cuprous oxide. SNS2, this is tin 4, which is the higher oxidation number, and so this is going to be stannic sulfide. And mercury 1 chloride would be hydrogerous chloride. Also, sometimes it's used mercurous chloride. Mercury was one of the first to switch over from the Latin. Polyatomic ions are ones where you have a combination of nonmetals that are covalently bonded together and overall have an excess of electrons. And then there's ammonium ion, which has a deficiency of an electron, but the same rules apply. Okay? You treat polyatomic ions as if they were monatomic ions. When you need more than one of the polyatomic ion, you put brackets around it, and then subscripts outside the brackets. So for example, if I take calcium 2 plus ion and phosphate 3 minus ion, when I combine them, it becomes Ca3PO42. and that would become calcium phosphate. Remember, if you have metals, cations that have the that are multivalent, so there's more than one possible charge, then I have to have the Roman numeral to tell me which charge I'm using on that particular cation. Now, the polyatomic ions you'll have on your periodic table a fairly extensive, it's not exhaustive, but it's a fairly extensive table for polyatomic ions. And what the best idea would be to memorize those that have the ATE suffix. Because you can figure out the ITE and hypoite and perite with the following pattern. They all kind of behave the same way. I don't have all of the versions on there, but you could easily figure that out if you apply the following criteria. So the ATE suffix, okay, is kind of the normal one. And this depends. It's not always the same number of oxygens here. So for example, sulfate is SO4 2 minus. Phosphate is at PO4 2 minus, 3 minus. And so this one here, chlorate, happens to be ClO3 minus, a 1 minus charge. So if you remove one of the oxygens from the normal one, then you get the ite. Okay, and so ClO2 1 minus now becomes chlorite. You'll notice it still has the same overall charge. I take away a second oxygen, then I get hypoite, so hypochlorite. If I add an oxygen to the main one, then I end up with perchlorate. All right, and all the other ones follow the same pattern. So sulfate, for example, would be sulfate, sulfite, hyposulfite, persulfate, same pattern. All right, as an example, this one here, MnO3 1 minus is the normal one. This is MnO4, so it's permanganate, so calcium permanganate. Sodium nitrite. Barium phosphite would have the formula Ba3 PO3 2. All right, for those compounds that contain hydrogen, there are a couple of special cases because we can have hydrogen as either the cation or as the anion, depending on whether what it's with has a higher or lower electronegativity. When hydrogen has the lower electronegativity, as it does with chlorine, then it comes first, takes the form of the cation, and it becomes hydrogen chloride. If it has a higher electronegativity, like it does when it's with lithium, then it becomes the anion, and we get lithium hydride. Right? So trying these few, HBr then, it's hydrogen bromide. MgH2 would be magnesium hydride, and hydrogen sulfide would be H2S. Acids, there's a couple of different groups of acids. We have, first of all, the haloacids, and this is where we combine hydrogen with one of the halogens and then dissolve it in water. Remember, acids always have to be dissolved in water, and so the AQ symbol always has to be there to indicate the acid. So the basic compound is just hydrogen and one of the halogens, so hydrogen and fluorine as an example. Hydrogen and fluorine would be hydrofluoric acid. Okay. With bromine, would be hydrogen bromide, and then dissolved in water, it becomes hydrobromic acid, or hydrochloric acid, or hydroiodic acid. There's all the scenarios. The oxyacids are kind of the polyatomic ions that have oxygens in them. And when you put them with hydrogen, then you get uh, you just basically name it hydrogen sulfate. And so now when you dissolve that in water, it becomes an acid, and now it follows the same pattern as the naming of the polyatomic ions did in the first place. The difference then is the ik and is, right? So the 8, so let's say sulfate ion with hydrogen becomes sulfuric acid. The nitrite ion becomes nitrous acid. The chlorate, hypochlorite ion becomes hypochlorous acid. The perchlorate ion becomes perchloric acid. And those are that's the pattern that we follow for those acids. Homework, page 70, numbers 7 to 12. Work on those for a bit. There are ionic compounds that have crystal structures which have lots of holes in them. So as I explained in class, you form these large ionic networks, which are positive ions surrounded by negative ions and negative ions surrounded by positive ions. And in the process of that crystal structure building up, sometimes the configuration allows for these holes which allow water to be trapped inside them. And what it does to the crystal is that it actually makes it a nice vibrant color. So instead of being a dull gray blue, which is normal copper 2 sulfate, for example, um, it becomes, once it's hydrated, it becomes a bright royal blue. The example here, cobalt 2 chloride, um, normally is just kind of a dull pinkish, pinkish gray color. But when you hydrate it and you incorporate the water molecules into the crystal structure, then it becomes a really bright, vibrant red. So this compound now, we just call it based on the normal ionic name, so cobalt 2 chloride, and then with however many waters, and we call it dihydrate. So we use the mono-di-tri prefixes for the number part, and then the water just gets the name hydrate. For naming compounds that are covalent or molecular in nature, remember we add the prefix which indicates the number in the compound. So there's 2 nitrogens, 3 sulfurs in this example. It becomes dinitrogen trisulfide. If there's only one of the first one, we don't bother with the mono. We just call it carbon tetrachloride. In case you need the prefixes again, because you don't remember from grade 9 and 10, here they are. Make sure you have them memorized. All right, so N2O5. What do we call that? Dinitrogen pentaoxide. Phosphorus pentachloride. SiBr4. Okay. All right, so try some of those questions. See how well you do.